Up to this point, we have been discussing time-independent perturbation theory. In that framework, the perturbation does not explicitly depend on time, and our main goal was to determine how the stationary energies and eigenstates are modified by a weak static perturbation. Now we move to a different and equally important situation: time-dependent perturbation theory. This is the framework we use when the perturbation changes with time. Physically, this means the system is being driven by some external influence that varies in time. For example, an oscillating electric field, an electromagnetic wave, a pulsed excitation, or some switched interaction. In such cases, the main question is no longer just how an energy level shifts. Instead, the central question becomes, how does the system evolve in time, and how does it make transitions from one unperturbed state to another? So this part of the chapter is really about transition dynamics. In time-independent perturbation theory, we obtained corrected eigenenergies and corrected eigenfunctions for a stationary or nearly stationary problem. Here, in time-dependent perturbation theory, we typically start from a known unperturbed basis and then ask how the amplitudes of those basis states change with time under the action of a weak time-dependent perturbation. This is a very important conceptual shift. In other words, instead of solving for a new stationary eigenstate, we now solve for a time-dependent superposition of known unperturbed stationary states. The perturbation couples those states together, and their coefficients become functions of time. So you may think of the chapter flow in this way. First, time-independent perturbation theory told us how weak static perturbations shift energy levels and distort states. Now, time-dependent perturbation theory will tell us how weak time-varying perturbations drive the system from one state to another. This is the starting point for understanding induced transitions, absorption, emission, and eventually harmonic perturbation and Fermi's golden rule. So from here onward, please keep one phrase in mind. Time-dependent perturbation theory tracks the time evolution of state amplitudes in a known unperturbed basis. Let's now set up the perturbed time-dependent problem. We start from the time-dependent Schrödinger equation for a perturbed system. The Hamiltonian is assumed to have the form as shown, where lambda is again the perturbation parameter and will be set to 1 at the end. Here we use the calligraphic H prime to distinguish the time-dependent perturbing Hamiltonian operator from the known unperturbed time-independent Hamiltonian operator H hat naught. The perturbative condition is explicitly given by this inequality, which says the perturbation is assumed to be weak in the sense that its matrix elements between unperturbed states are sufficiently small compared with the relevant energy separation, so that the induced corrections or transition amplitudes remain small and perturbation theory remains valid. So the structure is similar to what we used in the time-independent case, except now the perturbation explicitly depends on time. We assume that the unperturbed Hamiltonian operator H hat naught is time-independent and that its solutions are already known. So its stationary eigenfunctions satisfy the eigenvalue equation for the time-independent Hamiltonian operator, as shown in this equation. And these eigenfunctions form a complete orthonormal set. From these stationary spatial eigenfunctions, the full unperturbed time-dependent solutions are given by this formula, which is just the usual stationary state time dependence that we discussed earlier in quantum mechanics. Therefore, the most general solution of the unperturbed system can be written as this formula, where the coefficients a sub n naught are constants for the unperturbed problem. So let me emphasize the picture here. The unperturbed system gives us a complete set of non-stationary solutions. Those solutions form the natural basis in which we will describe the perturbed time-dependent system. So here comes the key strategy. We do not try to solve the full time-dependent Schrödinger equation from scratch in coordinate space. Instead, we expand the involving wave function in the non-unperturbed basis and then solve for the time dependence of the expansion coefficients. That's exactly what will happen on the next slides. Now we write the wave function of the perturbed system as a superposition of the unperturbed stationary solutions, but with coefficients that are allowed to vary with time. So we have the expansion shown here. This is the central idea of time-dependent perturbation theory. Notice the key difference from the unperturbed case. Previously, the coefficients were constants. Now, because the perturbation depends on time and can couple different states, the coefficients a sub n of t become time-dependent. Also, because the state is expanded in the orthonormal basis of unperturbed states, the absolute square of the time-varying coefficient a sub n of t is the probability that a measurement finds the system in the nth unperturbed state at time t. So physically, the perturbation doesn't destroy our basis. It remains to be the eigenbasis of the unperturbed time-independent Hamiltonian operator. Rather, it causes the amplitudes of the basis states to evolve in time. So if the wave function is normalized, then this equation must hold, which means the sum of the absolute squares of all expansion coefficients must be 1. For the unperturbed system, the analogous condition is shown here. So now our entire task reduces to finding out the functions a sub n of t. Once those amplitudes are known, the time evolution of the system is known. This is a major conceptual simplification. Instead of solving directly for the full space and time-dependent wave function, we solve for a set of time-dependent amplitudes in a known basis. So from this point on, time-dependent perturbation theory becomes a theory of coupled equations for the coefficients a sub n of t. Now we substitute the expansion of psi of Rnt into the full time-dependent Schrödinger equation. On the right-hand side, we need to apply the product rule for the partial time derivative of psi of Rnt because it involves the time-varying coefficient a sub n of t and the temporal part of the full unperturbed eigenfunction. Therefore, we get partial over partial t a sub n of t in the first summation term and the partial time derivative of the full unperturbed eigenfunction in the second. Now for each unperturbed full eigenfunction capital phi sub n naught, since its partial time derivative gives this expression, after multiplying by minus h bar divided by I, we obtain e sub n naught times the full unperturbed eigenfunction, which is equal to the unperturbed Hamiltonian operator acting on the full unperturbed eigenfunction, as shown. Therefore, the first summation term on the left-hand side cancels the second summation term on the right-hand side. Next, we project the resulting expression onto the nth unperturbed time-dependent bra state, or equivalently take the inner product with the full wave function of the nth unperturbed state as shown. Using orthonormality, we can further simplify this equation involving the phase factor e to the I omega sub mn t, where omega sub mn is the Bohr angular frequency associated with the energy difference between states m and n. That is a very important physical quantity. It will later play a central role in resonance conditions and transition probabilities. So this slide is the technical derivation step. We substitute the expansion of the full perturbed wave function into the time-dependent Schrödinger equation, cancel the unperturbed evolution of eigenfunctions, project onto a specific unperturbed time-dependent bra state, and isolate the equations that govern the time evolution of the coefficients a sub n of t. The next slide writes the final result in compact form. Using the orthonormality condition on the equation obtained from the previous page, we can remove the summation over n after replacing n by m. This leads us to the fundamental result of time-dependent perturbation theory, that is, the time rate of change of the coefficient a sub m of t, where the formulas of the perturbation matrix element h sub mn prime and the Bohr angular frequency omega sub mn are respectively shown here. This is the central working equation. Let us interpret it carefully. The left-hand side, d over dt a sub m of t, is the time rate of change of the amplitude associated with the nth unperturbed state. The right-hand side tells us that this rate of change is driven by a sum over all other states n. Each term is weighted by 3 factors. First, the current amplitude of state n, a sub n of t, which tells us how much of state n is already present. Second, the perturbation matrix element h sub mn prime, which tells us how strongly the perturbation couples state n to state m. And third, the oscillatory phase factor e to the I omega sub mn t, which tells us the energy difference between the two unperturbed states. So this single compact equation is actually a large coupled system of equations, one equation for each m, and each equation depends on all the coefficients a sub n of t. Physically, this is the essence of time-dependent perturbation theory. A time-dependent perturbation couples the unperturbed states together and causes probability amplitude to flow from one state to another. This equation is also the starting point for the approximation schemes that follow. In practical problems, we often assume that initially the system is in one particular unperturbed state, and then solve these coupled equations approximately to determine the probability of transition to other states. So if you want one sentence to summarize the entire slide, it is this. Time-dependent perturbation theory converts the Schrödinger equation into coupled differential equations for the amplitudes of the unperturbed basis states. On the previous slide, we obtained the fundamental result of time-dependent perturbation theory. The product of A sub n of t, perturbation matrix element, and the exponential phase factor represents the contribution from state n to the time evolution of the amplitude of state m. The factor A sub n of t tells us how much of state n is currently present. The matrix element H sub m prime of t tells us how strongly the perturbation couples state n to state m. And the exponential phase factor reflects the energy difference between the two unperturbed states. For each state m, the time rate of change of its amplitude is determined by or coupled to the amplitudes of all the other states through the perturbation matrix element. So the amplitude of a given state doesn't evolve independently. To make the structure completely visible, we write this compact equation out in explicit form for several amplitudes, such as A naught of t, A1 of t, and a general A sub m of t. Note that in the matrix element H sub m prime of t, the second subscript n labels the unperturbed state being summed over. That summation runs over the complete orthonormal set of eigenstates of the unperturbed system. By contrast, the first subscript m identifies the state whose amplitude A sub m of t we are solving for. Since m can represent any unperturbed eigenstate, it must also run over the full set of unperturbed states. Therefore, if the system has only a few relevant states, then this is a small set of coupled differential equations. But if the system has many eigenstates, then the equation actually represents a very large system of coupled equations. For example, if we restrict ourselves to a system with 100 discrete unperturbed eigenstates, then we obtain 100 coupled equations, each with 100 terms on the right-hand side. That's why we say that this is mathematically accurate, but solving it directly can become quite tedious. So this slide makes the coupling picture very concrete. Every state talks to every other state through the perturbation. This is also a good moment to emphasize something physically important. Time-dependent perturbation theory is not primarily about shifting one energy level. It is about transferring amplitude and probability among states. That's why the time derivatives of the coefficient A sub m of t are the central quantities here. So the main takeaway from this slide is the compact amplitude equation is actually a coupled system of many equations, one for each unperturbed state, and solving that full system exactly is generally difficult. That's why we now turn to a perturbative approximation for the coefficients themselves. Since solving the full coupled system exactly is generally too difficult, we now apply perturbation theory to the coefficients themselves. We write each amplitude as a power series expansion in the perturbation parameter as shown. This is completely analogous to what we did earlier in time-independent perturbation theory. except that now the quantities being expanded are time-dependent amplitudes, a sub n of t, not stationary energies or stationary wave functions. The zeroth order term, a sub n naught of t, describes the amplitude in the absence of the perturbation. On the next page, we will show that it is independent of time. The first order term, a sub n1 of t, is the leading correction caused by the weak time-dependent perturbation. The second order term, a sub n2 of t, is the next correction, and so on. In first-order time-dependent perturbation theory, we keep only the first correction term because it is assumed to be the dominant perturbative contribution. We now substitute this expansion to the second order of lambda into the coupled equation for the nth amplitude. After substitution, both sides become power series in lambda. Then, just as in ordinary perturbation theory, we equate coefficients of equal powers of lambda. That procedure will generate a hierarchy of equations, a zeroth order equation, a first order equation, and if desired, higher order equations. We'll see those equations when deriving the zeroth order, first order, and the higher order solutions later. Before we wrap up this slide, I want to highlight one more important point. In the equation for the time rate of change of the nth amplitude, the indices m and n run over the complete set of unperturbed eigenstates. Whether they start from 0 or from 1 depends on how the unperturbed eigenstates are labeled. There is no universal rule that they must start from 0 or from 1. For example, in a harmonic oscillator, m and n start from 0, but in an infinite potential well, they start from 1. In a word, the indices m and n run over all unperturbed eigenstates, and their starting value depends on the indexing convention adopted for that particular system. So this slide is the setup for the perturbative approximation. Instead of trying to solve the entire coupled system exactly, we solve it order by order in the small perturbation parameter lambda.